Okay, I think we can get started. Can everybody see my slides? Good. All right. So today we are going to actually talk about proofs. Towards the end, we have a few questions on proofs on sets, but actually majority of the time we might be spending on just general proofs and quick review because that's what's going to be on quiz number 2. All right, so some announcement. We are currently grading homework 2. Quiz 1 score is already out. So remember about our regrading policy. You have 1 week from receiving your grade to request any regrade for the quiz. Very importantly, quiz number 2 is next week on next Tuesday. Please mark on your calendar. Do not forget, we have another quiz coming up. For total, this class has 5 quizzes and plus a final. So on average, we have a quiz every 2 or 3 weeks. Okay, so it's the same as quiz number 1. You're going to have 1 hour window between 7:30 until 4 p.m. So you should try to set aside this 1 hour to do your quiz. The difference from quiz number 1 is we have extended the grace period to be 30 minutes, meaning that you spend the first 1 hour try to solve the quiz, and then the remaining half hour, you should dedicate that to figure out how to upload your quiz to the Gradescope correctly. For example, you need to upload your signed page, your index card, and your solution, match your solution to the outline. Okay. And quiz number 2 is going to be on proofs, which is chapter 2 of the textbook. And also fair warning, this is one of those hardest quiz among all the quiz you're going to see. And so you should spend quite a bit of time preparing for it. And of course, read the syllabus and announcement carefully following about the quiz. Another thing is that quiz number 3 is also out. Homework 3 is out, and it's due on October 9. So we give, usually homework is due every 2 weeks. We give this one 3 weeks so that you have time to focus on preparation for quiz number 2. Okay. All right, any questions? Well, okay. All right, assuming there's no question, we're going to go through some practice. Yes, one important part is only for quiz 2, any request for makeup quiz has to do with some documented medical emergency. So you should read our policy carefully. So we will not accept any excuse of that is related to students not being able to figure out how to submit over Gradescope. Which is quite a bit problem for quiz number 1, but quiz number 2, we hope that you have figured out how to use Gradescope properly for our quiz submissions. Okay, let's do the first few reviews. To prove anything related to sets, there are some basic set properties we're going to use. One is subset property. So if A is a subset of B, it means for any element in A, it's also in B. However, if I use the proper subset symbol, which is this symbol, it means not only A is a subset of B, but also there exists an element in B that is not in A. So if I'm thinking about Venn diagram, for proper subset, this is how they are situated, especially somewhere here, there's an element in B that is not in A, okay? The last one is when 2 sets are equal, that means for all element in A, if and only if it's in B. That means if there are element X in A, it's in B. If there's element in B, it's in A. So the most important part of understanding this definition is it's equivalent to say that if A equal to B, that means A is a subset of B and B is a subset of A. And this is in fact the property that you're going to use when you prove set equivalences. Okay, so if I want to say, hey, prove to me the following 2 sets are equal, then most likely you're going to say, I'm going to prove, if I want to prove A is equal to B, I'm going to prove A is a subset of B and B is a subset of A. So that implies A is equal to B. Of course, there's other symbols, which is empty set. Empty set contains no element. And then finally is a concept of universal set, which is sometimes called universe. It's a set that contains all possible elements And every set is a subset of the universal set. Of course, whenever we talk about the universal set, it's always within the context of the current problem. For example, if the current problem is talking about sort of the set of real numbers, then sometimes we will specify the universal set is sort of, let's say if my set I'm talking about is even and odd, then the set of universal number we're talking about is going to be integers. So usually the universal set is more clear in the context of the particular problem. Okay, let's do the first one. This one has nothing to do with sets. In fact, the next few problem is more of a practice problem for getting ready for quiz number 2. So you have 1 minute to think about how to prove by contradiction that there's no two integer x and y such that 24x plus 12y is equal to 1. Okay. So usually when you prove by contradiction is to assume whether there exists a counterexample. And then assume there's a counterexample and prove the counterexample does not exist because it leads to a contradiction. Then the original statement is true. Okay. So for this problem, what you want to start thinking about is what is going to be a counterexample, and how do you prove that counterexample leads to a contradiction?
So, Bei, there's a question about recitation sessions next week.
Mm-hmm.
Is there going to be a recitation session next week because of
no.
Okay.
No. So whenever we have a quiz, on the day of the quiz, which is a Tuesday, we will not have recitations. Because the argument would be that if this were in person, you would spend the time during recitation to try to do your quiz. That's why the quiz is have a length of an hour. So you can find at least 1 hour to do your exam. You can use the recitation time, but there's no actual lectures. All right. Anyone want to volunteer? What is how you would prove this? What is a counterexample? Anyone? If the problem statement is there are no two integers x and y such that certain probability, yes, go ahead, Cameron.
Okay, so if you factored out a 2, you would have 2 times 12x plus 6y. Mm-hmm. And then you could, under closure, have that be an integer. So you'd have 2 times an integer equals 1, and 1 is not an even number, so it's a contradiction.
Cool. So you kind of just went through the entire proof, right? But no, that's great. It's great. But to start your proof, you want to assume there exists a counterexample, right? And that counterexample is there are two integer x and y such that 24x plus 12y equal to 1. And then we can proceed with your proof. Okay?
Okay.
So yeah, but yes, your proof really has the key point of this problem. So assume a counterexample exists. So that means exist x and y, which are both integer, such that 24x plus 12y equal to 1. First, we assume a counterexample exists, and we prove this leads to a contradiction. So I'm going to, like you said, factoring 2. So you have 2 times 12x plus 6y equal to 1. And now, by closure property of integer under addition, let k equal to 12x plus 6y. K is an integer. That's by closure property. So we have 1 is equal to 2 times k, right? I do some rearrangement. So this means, where k is integer, this means 1 is even, which contradicts to the fact that 1 is odd. Contradicts to the fact that 1 is odd. So therefore, counterexample does not exist and the original proposition is true, which means there are no two integers such that 24x plus 12y equals 1. So I kind of added a little bit more detail on top of your proof, but yes, your proof was correct. All right, let's look at the next one. And this is one we actually kind of went through before. So I would like to just give you sort of 1 minute to think about the 4 steps of induction proof, okay? So whenever you have induction proof, and this is a very typical form of induction proof, which is involving proof related to a sequence. So you are going to use some basic algebra manipulations. Specifically for this particular problem, we actually provided a hint, which is x minus 1 to the power 5th. You can expand it with all this coefficient that's provided. Okay, so when you have induction proof, what you're going to always have is what's a problem statement, what is a base case, what is induction hypothesis, and finally, what is induction statement. Okay, so and the most important part of induction proof is that if somewhere in your actual induction step, right, induction step, that you're not using induction hypothesis, then something is not right. So somewhere in your induction step, you are using induction hypothesis. Okay, so do I have a volunteer to first tell me what is a problem statement? What do I want to prove? You can raise your hand and then you can unmute yourself. Well, pretty much this problem is already stated, right? For the problem statement, I want to show that for or integer that is big or equal to 1, I want to prove 5 is can divide n to the power 5th minus n. This means that n to the power 5th minus n is equal to 5 times, let's say p, for some p that's integer. So this is just using the property of something divisible by 5. And then this form is actually easier to use later, but it's equivalent. So what is the base case?
When n is equal to 1.
Okay, say it again.
When n is equal to 1.
But that's only the first half of your base case. When n is equal to 1, what do you want to prove?
That's divisible by 5, sorry.
Yep, exactly, right? So you just set the condition of what is the variable value at the base case, but you want to show when n is equal to 1, 5 divides n to the power 5th minus n, right? That's what it is. So when I substitute 1 into it, so that means 1 to the power 5th minus 1 is equal to 0, and that is 5 times 0. So therefore, 5 divides 1 to the power 5th minus 1, right? So to simplify, I'm going to say P of n is what's in that box. P of n is a proposition for or n equal to 1, 5 divides by n minus 5 minus n. So essentially what we're showing is show P of 1 is true. That means when n is equal to 1, 5 divides n to the power 5th minus n. So now, what is induction hypothesis? What do we assume? Anyone? Jose, go ahead.
Assume n minus 1 is true.
Okay, assuming the proposition is true for n minus 1, so alternatively, that means assume p of n minus 1 is true. And what does that mean? That means 5 divides n minus 1 to the 5 minus n minus 1. Also, that means n minus 1 to the power fifth minus n minus 1 is equal to 5 times p, or let's use some other variable, let's say q, for some q that's integer. Okay, so that is the hypothesis. And now you are getting close, because this is the most important part as part of induction hypothesis. Okay, is assuming this equation hold. So can someone tell me what you want to prove in the induction step?
Just prove that p of n is true.
Yep. So of course, when I say p of n is true, I need to spell it out. That means 5 divides n to the power 5 minus n. Okay, do I have anyone who tell me where do I go from here? And then this is the most tricky part of this problem. I think I have Jose raising hand. Go ahead.
Just use the binomial theorem with n minus 1 to the fifth.
Mm-hmm. How would you do it? Are you saying you're going to substitute this term?
Right.
Okay. Yeah, that's exactly. But the rest is really algebra now. So how do we think about this? The induction hypothesis, which is highlighted in yellow, describe to me the relation between n minus 1 to the power fifth minus n minus 1. But what I want to show is n minus 5 minus n is equal to 5 times p for some p equal to integer. So now I have two expressions, the one in yellow and then the one in green. So how do I relate those two expressions is to through the hint. Okay, so let's do it. So because using induction hypothesis, I have n minus 1 minus 5 minus n minus 1 is equal to 5q. What I'm going to do is I'm going to expand the left term, which is n minus 1 to the power fifth, to be the one on the right hand side by the hint. So I get n to the power fifth minus 5 n4 plus 10 n3 minus 10 n2 plus 5n minus 1 minus n minus 1 is equal to 5q. Okay. And now, since I'm running a little bit out of space, I'm going to do some rearrangement. Because once I expanded the term, I get the term n minus 5 here. I also get the term minus n here. So I can keep those two terms on the left-hand side of my equation and move everything to the right. So just a rearrangement. So I get something like n to the power fifth minus n is now equal to 5 times q plus 5n4 minus 10n3 plus 10n2 minus 5n. And then I can factor out a 5, which is q times n4 minus 2n3 plus 2n squared minus n. So now what you can say is by closure property of integers, I can set everything in the parentheses to be p, and the p is an integer by the closure property of integer under addition, multiplication, and subtraction. So now n to the power fifth minus n is equal to 5 times p, which means that n to the power fifth minus n is equal to is divisible by 5. So that's the end of the proof. Okay, so everything I wrote here is a sketch, and here is a detailed proof. Okay. The most important part of this proof is really the part that when you use induction hypothesis here, when you're using induction hypothesis, you kind of expanded this formula using the hint that's provided. Okay, and then this is probably the most tricky part, because once you use that, then the next step is to focus on the few terms, this term and this term, which is already part of my induction step. And you're using a lot of algebra to try to arrive at that form. So really the key idea is how do I go from a formula that describes this term to a formula that describes this term. And that's based on algebra. Okay, any questions? All right, the next practice, we're going to review quickly the pigeonhole principle. And again, this is a problem you might have seen before. If I have 7 integers, I want to prove there will be 4 of them such that the sum of the square of those integers is divisible by 4. So whenever you want to use a pigeonhole principle, you want to essentially ask how many objects are there, how many containers are there, and for at least one of the container, how many objects that falls into that container. Okay. So can someone tell me how many objects do I have for this problem? And keep in mind that this pigeonhole principle is part of chapter 2, which likely will show up in the quiz. It's sort of already stated in the problem, right? Giving you 7 integers, that is total number of integers you have. So you have mn plus 1 equal to 7. Okay, so I don't know how many containers I have yet, but the problems tells me it's interested in looking at 4 of those integers. So if I'm thinking about pigeonhole principle, then there is 4 elements or 4 objects that will force into a container to have this particular property. Okay, so what I have is m plus 1 equal to 4. This is for at least one of the container, there's 4 of those integers. So those are already given to you by the problem itself. So can someone tell me how many containers, if I know those 2 equations, what is equal to, how many containers do I have?
2.
2? Yeah, you're just solving for 2, okay? So now I'm not done yet, right? Because there is this part where we want to prove the sum of the square of those integers is divisible by 4. And I said 2. So the next step is to how to design these containers, these 2 containers. Okay, so I have 2 containers. How do I design it? Okay, we're dealing with integers. So do I have any volunteer? Say how do I design the containers? You can type or you can raise your hand and then unmute yourself. Okay, so Yoking, you really should read what's the comments is for me.
Yeah, there is just one suggestion saying we should make them even and odd.
Okay, all right. I think Peter made the suggestion is even and odd. Let's see if that works. Okay, But okay, in the future, you should read those. So because I wouldn't be able to check it quickly, you should help me monitor this. Okay. All right. So let's go over this particular one. Let's say if I define its integer even or odd, and if I'm dividing them by remainder, it means it's remainder of 0 or remainder of 1 if I divide them by 2. Okay. So case number 1, let's say those are my containers. Then case number 1 is all numbers are even. So that means there's 4 even numbers. Then I can have A equal to 2m, B equal to 2n, C equal to 2k, and D equal to 2l. Because they are all even numbers, that falls into the first container. Now I just need to do a squared plus b squared plus c squared plus d squared is equal to 4m squared plus 4n squared, 4k squared from 4l squared. And you can factor out of 4. And then the rest is closure property. Okay, so of course I'm writing sketch right here. So that means it's divisible by 4. Case number 2, or numbers are odd. So you have A equal to 2m plus 1, B equal to 2n plus 1, C equal to 2k plus 1, D equal to 2l plus 1. Okay. And you're going to do the same thing as I did before. I'm just going to take what is a squared plus b squared plus c squared plus d squared. In this case, what you can do through some expansions and factor out of 4, you get something like 4 times m squared plus m plus n squared plus n plus k squared plus k plus l squared plus l n plus 1. But still, you can factor out of 4, and by closure property of integer is divisible by 4. So yeah, so this is the right version, but also there's actually a separate version which uses what the problem is asking, right? Because the problem is asking whether it's divisible by 4, and you have another alternative solution, even though this alternative solution is a little bit longer to prove. Does anyone has idea what is my alternative solution to this problem? Because the problem is asking whether it's divisible by 4. So one thing come to my mind is how to design containers based on the remainder once divided by 4. So when a number is divided by 4, it has a few remainders, right? 0, 1, 2, or 3.
Yeah, so we have a suggestion like saying if we have 4 boxes, like one for like divisible by 4, and then one is like remainder is 1, 2, and 3.
Yep, perfect. Okay, so this is what we have. Your second version is you can have 2 container based on the remainder of the integer divided by 4. So it can remainder of 0, 2, or 1, 3. And in this particular design, you can also prove the problem statement, except the number of cases is much larger. Because if you have 4 integers falls into, say, the first container, then their remainder is either 0 or 2. So there's multiple combinations. Similarly, with if you have 4 integer falls into a second container where the remainder is 1 or 3. But you can still achieve at the final results with more case studies. Okay. All right. Now let's look at a proof involving sets. So prove that the set, let's call this first set, set A, which is 4m. And then let's call the second set B. We want to show the first set is a subset of the set B. Okay. Do I have a volunteer how to prove this? And I will tell you the proof in here is 1 line. Okay, so I see someone on the chat.
Yeah, we have a suggestion saying.
Yoki, please help me keep track of the chat. I just saw the chat. So from Peter, it says 4m equal to 2n. So that's a rough idea, but this is not really how you would write the proof. Can you expand it further? Okay, so I saw Elizabeth in the chat to say 4m is equal to 2 times 2m. Exactly. So really the proof is one line because it's relying on factorization. Okay. So in order to show, so both Peter and Elizabeth is correct, but Elizabeth, you gave a little bit more information. And Andrew said there exists an element in B for 4m. I'm not sure what that means. If I want to show A is a subset of B, I'm going to start from an element in A and show that an element in A is in B. Maybe that's what you mean. Okay, so let's look at this proof here. So basically what we need is to say, let X in A, right? By definition of the set A, X is equal to 4m for some m in integer. And then the only step I need is factoring, which is what pointed out by Elizabeth. And of course, when I'm factoring, I will say by closure property of m of integer, under multiplication, let k equal to, well, in this case, k equal to 2m and k is equal to integer. So x is equal to 2 times k for k some integer. And this means X is also in B. So I start with element in A. I showed it in B. That means A is a subset of B. So actually just say therefore A is a subset of B. Okay, good. So this is really the sketch. Let's look at the next one. I want to show if B has no element, then B is a subset of any set A. Okay, so B has no element, that means B is empty set. Okay, so I want you to prove by contrapositive. So again, this proof is maybe one line. It's also roughly one line of proof. Right? Since we're proving by contrapositive statement, can you tell me what is a contrapositive statement? Do I have a volunteer? Okay, I see Dylan raised hand. Please go ahead. Unmute yourself.
So if P implies Q, then the contrapositive statement would be not Q implies not P. Yes. Yeah.
P implies Q, not P implies not Q implies not P. But what is English statement here? What is a statement?
Oh, for the problem?
Yes.
So if a wait, for a contrapositive, would you flip the subset in the domain for the then statement?
So like you said, this is P, this is Q, right? So the original statement is P implies Q. The contrapositive, like you said, is not Q implies not P. So what is not Q?
Would it be if B is not a subset of A?
Yep.
Okay, then B has elements.
Has at least one element.
Yeah, at least one element.
Yep. Okay. That is a contrapositive statement. Once you prove this is true, the original statement is true because those two things are logically equivalent. Okay. So can someone tell me what is a sketch of this proof? Do I have volunteer? You can raise your hand using Zoom, or you can type, or you can unmute yourself. Okay, so I see that over chat,
Yeah, we have a
Peter said B has elements not in A. By definition, B has no element. Okay, so okay, that's roughly the idea. But for the actual proof, I mean, I think you have the right idea. But for the actual proof, let's write it in a little bit more detail. Okay, so we can say suppose B is not a subset of A, which is what you wrote. B is not subset of A. That means then by definition of not a subset, right? This means there exists an element X that is in B and it's not in A, right? Because B is not a subset of A, that means there's some element in B that's not in A. But like you said, because of this, X is already in B. That means, so X in B means B is not empty. That is the end of the proof. So X is the element that is in B, right? Because a contrapositive statement is asking, the contrapositive statement is saying that if B is not a subset of A, then B have at least one element. We just use the definition of a subset. It means there exists an element that is in B but not in A, but because X is in B means that B is not empty. So B has at least one element. That's the end of the proof. Okay. All right. So next one, and this is the last question of this recitation, is I would like you to prove the following statement by two different ways. One, proof by contrapositive statement, and then two, proof by contradiction. And I'll give you 2 minutes to try to write both type of proof. Again, for each proof, I think it's roughly 3 lines of proof, but it's a very good practice for you to get a sense of the difference between proving by contrapositive statement and proof by contradiction. Okay, there's a question over the chat. This is not divide. This means the difference between the two sets. It means everything is in A but not in B. So in set notations, this means everything is in A but not in B. Okay, do I have a volunteer to show how to prove this problem by contrapositive statement? What is a contrapositive statement? right? Remember, P implies Q. The contrapositive statement is not Q, implies not P. So this is my P statement. This is Q statement.
Would that be A divided by B is not equal to an empty set? Then A is not a subset of B?
Mm-hmm. So let's say if A difference B is not equal to empty set, then A is not a subset of B. Okay, good. Okay, so I think in the chat, there's someone, Peter said, the proof is to say A minus B not, well, actually that's also the contrapositive statement. That's fine. Okay, so anyone has idea how to prove this? Do I have a volunteer?
So there's a suggestion by Peter saying if A difference B is not empty, then there exists this X in A.
Okay, so great. So that's his rough idea. When I prove contrapositive statement, I'm going to make use of the hypothesis, right? Since A, the difference between A and B is not empty, okay? That means we have some element in A but not in B. So we have some X that is in A and it's not in B, because that is by definition when the difference between A and B is not empty. So because there's some element in A and not in B, therefore this particular element X, by definition of subsets, that A is not a subset of B, okay? Because when there's some element X that is in A, but is not in B, that means A is not a subset of B. So what Peter has typed is correct. Okay, next one. How do I prove by contradiction? Remember, if I want to prove by contradiction, I want to assume there exists a counterexample. Okay. So just recall, if I have P implies Q kind of statement, the counterexample is always in the form of P, not P and Q. That is how the counterexample looks like. Okay. Wait, sorry.
Oh, it is
I think it's P and not Q.
P and not Q, yeah.
Sorry for P and not Q. Okay. Anyone want to give it a try?
Would that be A is a subset of B and A divided by B is not an empty set?
Yes. So, but of course, in the actual proof, I need to spell it out. So suppose there exists a counterexample such that this counterexample is P and not Q. So A is subset of B, and the difference between A and B is not empty. Okay. So how would I prove that the counterexample does not exist? So again, if you think about the previous proof, we have to somehow use a property of the difference, right? So I need to use some difference here. And again, the proof is by contradictions is also 2 lines here. And then this is an interesting problem because once you kind of convince yourself there's two different type of proofs, it helps you, you know, whenever you look at a problem is how to get to different ways of solving the problem. Yeah, go ahead. I think Peter typed in X is in A implies X in B and exists X in A and not in B. Okay, so let's use a property as you said. Let's assume because this is part of the counterexample. So since the difference between these two is not empty, then we have some element X that is in A and not in B. Well, first of all, this is part of A-B difference. And by definition of the set difference, X is in A and not in B. What is the next step? Where does the contradiction come from? I just figured there's an element in A but not in B. What does this mean? We already used this part of my counterexample, the difference. So somehow I need to use this. Means that I want to create a contradiction with this statement, right?
I think there are like two answers. I think Peter said the same thing as well. So it basically says there's, since A is a subset of B, then all the elements must be in B as well. So, and there's a contradiction kind of there.
Wait, so Peter said in the chat, although Andrew said in the chat, since A is a subset, all its element must in B. The contradiction is that there is an element in B and not in B. Wait, so A is a subset, all its element must in B. The contradiction is that there is an element in B and not in B. Okay, that's a one way to put it, and it's correct. There's also another way to put it. Alternative way is to say that, well, because I found X is in A and X is not in B, that means it follows that A is not a subset of B, which contradict to A is a subset of B. So that's a contradiction, okay? So what you said is a good contradiction too. And then what I wrote here is another alternative contradiction, right? So because there is a contradiction when your counterexample, then that means the counterexample does not exist, which means the original statement is true, okay? And if you want to challenge yourself further, my next question for this problem is term of take home is, can you use direct proof for this question? I don't know how hard it is, but it's a question to ask yourself, can I use some form of direct proof to prove this? Okay, so we actually managed to go through all the material for the recitation. Do you have additional questions regarding this recitation or regarding quiz number 2? All right. If there's no more questions, good luck with your preparation for quiz number 2. There's few places where you can get additional practice problem. The best way, students always ask me, how do I get ready for the quiz on proofs? The best way to do it is, number 1, try to do your practice quiz number 2. Set aside a time to do it within, say, an hour. See if you can solve all the problems and compare your solution with a provided solution set. That's one way, the first way to practice for quiz number 2. Second way is read the textbook. I will make announcement the exact chapters you want to read. I mean, it's essentially chapter 2, but if you want to know the sub-chapters, it's also stated in the module under Canvas. For each of the lecture associated with proofs, there is a section that talks about which chapter you want to read, but I will make announcement to summarize it. So read the textbook. The third one is at the end of each textbook chapter, there is problems that is in blue. So those problems are the ones that has a solution at the back of the textbook. So you can try to solve these problems and then compare your solution against the solution from the textbook. And of course, you want to go over your practice problem set for each of the problem set for each lecture, as well as the lecture slides and lecture videos. And then of course, come to office hours or go to Piazza if you have questions. Okay. All right. Good luck with the upcoming quiz, which is next Tuesday. Okay. Have a good day.